Pharmapal.
Pomegranate peel polyphenol. Welcome back to our channel. Today, we're diving into an intriguing study that explores the effects of pomegranate peel polyphenol on insulin resistance in rats with metabolic syndrome. Let's break it down. Metabolic syndrome is a cluster of conditions that increase the risk of heart disease, stroke, and diabetes. One key issue in this syndrome is insulin resistance, where the body doesn't respond well to insulin, leading to elevated blood sugar levels. Researchers in this study investigated how polyphenol from pomegranate peels could help alleviate this issue by promoting the insulin signaling pathway in skeletal muscle. Methodology overview. The researchers conducted their experiments using rats divided into groups. Some were fed a normal diet, while others were given a high-fat diet for 12 weeks. After this period, they assessed various health markers. Fasting blood glucose measurement. Blood glucose levels were measured biweekly from the rats' tails. Oral glucose tolerance test, OGTT. After fasting, rats were given a glucose solution to see how well their bodies could manage blood sugar. Western blot analysis. This technique was used to examine protein levels in skeletal muscle, helping to understand the effects of the polyphenol. Key findings. The results were promising. The study found that pomegranate peel polyphenol significantly improved insulin sensitivity in the skeletal muscle of the high-fat diet rats. This was indicated by enhanced insulin signaling pathways. Insulin signaling pathway. A series of biochemical events that occur in response to insulin, crucial for regulating blood sugar levels. Polyphenol. Natural compounds found in plants, known for their antioxidant properties and potential health benefits. Conclusion and implications. In conclusion, this study suggests that incorporating pomegranate peel polyphenol into our diets could be a beneficial strategy for managing insulin resistance and metabolic syndrome. While more research is needed, this could pave the way for new dietary recommendations that promote better health outcomes. Next, we'll explore the figures and tables presented in the paper, breaking down the results in a clear and engaging way. Let's get started. First up, let's discuss the statistical analysis used in this study. The researchers employed a one-way ANOVA followed by a least significant difference post hoc analysis to determine the significance of their findings. All results are presented as mean plus or minus SEM, which is a common way to express variability in data. Remember, a p-value of less than 0.05 indicates a statistically significant difference. Moving on to the results section, we see some fascinating data regarding the body weight and oral glucose tolerance test, OGTT, of the rats. Figures 2a and 2b illustrate that rats on a high-fat diet, or HFD, gain significantly more weight compared to those in the treatment and normal diet groups. In fact, by the end of the 12-week treatment period, the HFD group was 19.4% heavier than the normal diet group. Notably, the LPPPS and HPPPS groups showed a decrease in body weight by 12.4% and 15.8%, respectively, compared to the HFD group. These differences were statistically significant, with p-values of less than 0.01 and 0.001. Next, let's take a look at the gene expression data. The study provided forward and reverse primers for key genes like INS-R and IRS1. This information is crucial for understanding how PPPs might influence metabolic pathways. In section 3.6, the effects of PPPs on muscle glycogen and important proteins like GLUT1 and GLUT4 are discussed. These proteins play a vital role in glucose uptake, which is essential for energy metabolism. Additionally, the histological examination of skeletal muscle reveals significant differences in tissue structure between the groups, indicating that PPPs may have a protective effect against high-fat diet-induced changes. Now, let's turn our attention to Table 3, which summarizes the metabolic characteristics of the different groups. Here, we see values for fasting blood glucose, FBG, fasting insulin, FINS, insulin sensitivity index, ISI, and more. Each group shows distinct metabolic profiles, with the HFD group exhibiting elevated FBG and FINS levels compared to the normal diet group. Interestingly, the HPPPS group showed significant improvements in several parameters, suggesting that these polyphenol may enhance metabolic health. In conclusion, this study provides compelling evidence that PPPs can positively influence body weight and metabolic parameters in high-fat diet rats. The figures and tables we discussed today clearly illustrate these effects, making a strong case for further research in this area. Challenging questions and answers. 1. What is the significance of using a rat model for studying insulin resistance and metabolic syndrome? Rat models, particularly the Sprague-Dürly strain, are widely used in metabolic research due to their physiological similarities to humans. They allow for controlled experiments where researchers can manipulate diet and monitor physiological responses, making them ideal for studying complex conditions like insulin resistance and metabolic syndrome. 2. How do pomegranate peel polyphenol, PPPs, influence the insulin signaling pathway? PPPs are thought to activate key components of the insulin signaling pathway, such as PAR, peroxisome proliferator activated receptor gamma, which enhances insulin sensitivity. By promoting the phosphorylation of insulin receptors and downstream signaling molecules, PPPs can improve glucose uptake in skeletal muscle, thereby alleviating insulin resistance. 3. What were the main findings regarding the histological examination of skeletal muscle in HFD rats? Histological analysis revealed that rats treated with high doses of PPPs showed improved muscle morphology compared to those on a high-fat diet alone. This included increased muscle fiber size and reduced signs of inflammation, indicating that PPPs may help mitigate the damaging effects of a high-fat diet on skeletal muscle. 4. How does the dosage of PPPs affect their efficacy in alleviating insulin resistance? Answer: the study demonstrated a dose-dependent effect, where higher doses, 300 mg/kg BW/day, of PPP significantly improved insulin sensitivity compared to lower doses, 150 mg/kg BW/day. This suggests that adequate dosing is critical for maximizing the therapeutic potential of PPPs in managing insulin resistance. 5. What implications do the findings of this study have for human health and dietary recommendations? Thanks for joining us on this detailed exploration of the study. If you found this video helpful, please give it a thumbs up and subscribe for more content like this. Let us know your thoughts in the comments below.
Pharmapal.